we are dealing with sequences. We're working towards dealing with the convergence of sequences, being able to describe that in a rigorous mathematical way. So what did we do last time? Well, we started looking at one aspect of the long-term behavior of sequences last time, and that was whether sequences were increasing or decreasing. Such sequences that are either increasing or decreasing, they're termed monotonic sequences, which is the technical term. They're monotonic. They're always going up or always going down. And we did a little bit of an investigation on different ways you could prove or construct a kind of argument to say that a sequence defined by a given formula was increasing or decreasing. And we did this in two ways, by either examining the difference between consecutive terms, that's an plus 1 minus an, looking at the sequence an, looking at the difference between one term and the term that came before it, or we'd look at the ratio, an plus 1 divided by an. And if you look at the difference, you compare the difference to 0. You want to know whether that's positive or negative. That tells you which of the terms is the bigger. Or if you're looking at the ratio, and these terms are all positive, you want to be examining whether how the ratio compares to 1, or it's bigger than or less than 1. And that tells you which of the terms, either the top or bottom of the fraction, is the bigger one. So that's one aspect of the long-term behavior of a sequence, the behavior of the whole sequence. And just before we get on to the convergence, just another definition 1.4 in the notes. We say a sequence is bounded. A sequence is bounded if it's always trapped, or if it never strays beyond a certain fixed bound. Okay. So more formally, a sequence is bounded. A sequence xn is bounded if there exists some positive number n, such that the absolute value of the sequence elements is never greater than n. Now, the sequence elements xn could be positive or negative. That's why I'm talking about the absolute value there. So this number m, if this number m exists for a sequence, you can think of that the sequence is trapped between the values minus m and plus m. The sequence must live forever between those two values. If the sequence is like that, some sequences are, some sequences aren't, of course. If the sequence is like that, then we say it's bounded. And it can be a bit more descriptive by saying it's bounded above or bounded below. If there's a number m such that xn without the absolute values is always strictly less than m, then it's going to be bounded above. It might not be bounded below. It might reach large, unbounded negative values. On the other hand, maybe it is bounded below. Maybe there does exist a number n such that xn is always strictly greater than or equal to m. That would be it's bounded below. So again, this notion is referring to the whole sequence, the behavior of the whole sequence, not just the behavior of some collection of initial terms at the front of the sequence, but the behavior of the whole sequence. And when we get on to looking at convergence and look at examples of convergent and divergent sequences, we'll refer back to this notion of boundedness as well. It has a relationship to the notion of convergence. Okay, so now we want to start talking in detail about convergence. And we've already introduced the idea informally. We've said that convergence is when some kind of extended process or potentially infinite process is getting closer and closer to some limiting state. We see that in lots of areas. In the first lecture in motivation, I tried to describe areas in applied mathematics and pure mathematics where you can kind of see that and why it's an important concept. But coming down to more detailed context now, just talking about sequences of numbers, which we have been looking at, sequences of numbers. We say a sequence of numbers, so something like this, the sequence xn here in definition 1.5, we say it converges to the limit L if, as the index n increases, the elements of the sequence get closer and closer to this limiting value L. Or another way of saying that, an equivalent way of saying that, is the absolute value xn minus L Now that is the distance between the two numbers on the number lines, the distance between the number xn and the number xl on the number line, saying that that distance converges to 0. So you can either phrase it by saying, well, the elements xn are getting closer and closer to L, or equivalently, you can say, well, the distance between xn and L, that absolute value of the difference there, that's getting closer and closer to 0, converging to 0. Now, we'll see some examples in a moment. Just the kind of notation that we use, okay, we can either spell it out in English, as we have done in the definition 1.5, or we can also use some symbols to state the same thing. So this statement here in the middle, xn arrow L as n arrow infinity, that's saying that xn approaches L or converges to L as n tends to infinity. Now the way you would read that symbol, so the way you would read this line in English, when you see it on the page, you read it as xn converges to L as n goes to infinity. Or xn tends to L as n tends to infinity. That's how you read it off the page. Or alternatively, you could write something like the limit, this lim operator here. So this is kind of like an operator operating on the sequence element. And the lim, and it has this subscript underneath it, as n goes to infinity. The limit as n goes to infinity, the sequence xn is equal to L. That's how you'd read that second symbolic statement there, that second equation there. The limit as n tends to infinity of the term xn is equal to L. So those are convergent sequence. A sequence is convergent if such an L exists, if a limit exists for it. And we've spoken about a couple of examples in the previous lectures, and we'll speak more about them now. But if it's not convergent, then the technical term we use is saying that it's divergent. So if it doesn't have a final limiting value, we say it's divergent. Okay. Okay, so let's just put a little, let's make this a little bit more concrete by looking at some examples. Okay, so we're going to look at some convergence. We're going to observe, well, first of all, just observe the fact that all these sequences here, these are a bunch of sequences defined by these formula. You can take all of these formulae, 1 over n to some power. You can take that as the definition of a sequence element xn. And they're all converging to 0. So we've got 1 over n squared, 1 over n to the power 4, 1 over n to the power 6, 1 over the square root of n, 1 over n to the power 1/2, and 1 over n to the power 5th, or 1 over the fifth root of n. They all converge to 0. We can at least appreciate this when we look at their graphs. Sorry, when we look at a plot of some of the sequence terms. You can see this graph of dots here. So each color is one of the sequences. This is the index n running along the horizontal, and the value of the term xn is plotted against the vertical. They're color coded, so the blue one, this one here, this is the sequence 1 over n. So it starts off as 1, then it goes to 1/2, then it goes to 1/3, 1/4, 1/5, and so on. And it's getting smaller and smaller and smaller. And it's not too hard to appreciate that it's converging to 0. It's getting closer and closer to 0. The other ones, the green, red, and yellow, those are 1 over n squared, 1 over n 4, 1 over n 6. They're approaching 0 as well, and they're approaching much faster. Because the green sequence elements are less than the corresponding blue sequence elements. They're getting close to 0 faster. And then the red and yellow as well. But a couple of the sequences are converging to 0 much slower than 1 over n. So 1 over the square root of n and 1 over the fifth root of n. These are the ones in black and gray here. So the black one is the 1 over the square root of n. But the elements are still getting smaller, but at a slower rate. And even when you look at 1 over the fifth root of n, they're getting smaller, even slower. Now, if you look at some more of them, so m is the total number I'm plotting. You say, look at 200, So you start to see. I mean, you can barely even see the red and yellow ones because they get so small so quickly compared to the values of the other sequences. But you can see the blue 1 over n sequence. It's reaching very small values. The 1 over n to the power fifth, you know, it hangs around a bit. It's only getting small very, very slowly. Okay? But the more you continue, the more terms you plot. So if I increase this number m, the more terms I plot, the closer and closer the sequence elements at the end are getting to 0. Okay? So at least we're observing here convergent behavior. But now we're faced with a bit of an issue. Is that, okay? On the one hand, we can plot, you know, we can calculate values of a given formula. We can observe that they're getting smaller and smaller, say, when we're talking about converging to 0. But you know, maybe we'd want a stronger argument. Maybe we'd want an actual proof that they are converging to 0. But then, even more, these sequence definitions are, you know, of a fairly simple type, 1 over some power of n. We're going to meet sequences defined by more complicated formulae. So then the question is, well, how do we prove that such sequences defined by more complicated formulae, how do we prove that they're converging to something? Okay, because their values mightn't be so easy to appreciate. It mightn't be so easy to argue that. I mean, you can say these are all going to 0 because the denominators of the fractions are all getting bigger and bigger. They're all getting bigger and bigger without end. But moreover, rather than, as well as the problems posed by looking at individual sequences, if you just jump ahead in the notes a bit, as well as being able to deal with particular sequences, we also want to investigate the concept of convergence itself. And we want to prove things not about particular sequences, not only about particular sequences, but we want to be able to prove things about the phenomenon of convergence itself. And a few of those things are outlined here in these theorems. In particular, this one, theorem 1.1, we want to be able to show that limits are unique. Now, we'll be spending time with these, and we'll go through the detailed proofs of these in future lectures, but we can at least appreciate the statements here. That one, you may not have even have thought of that this needed to be proved, but this says if a sequence converges, then its limit is unique. If you do have a sequence that converges to some limiting value, then there can't be any other value that it's also getting closer and closer to. It's maybe not obvious, because maybe if you had two numbers, L and M, that were extremely close together, extremely close together, maybe a sequence could be getting closer and closer. Maybe a sequence could be converging to them both. But surely, you know, even if they're really, really close together, there's still an appreciable distance between them. So surely the sequence would have to make a decision at some point and go ahead and converge to one of them, and not the other. So we need to settle that issue. And then what's going to be very important for us is this algebra of limits theorem, which is a way that we can match convergent sequences, or we can prove how convergence fits with the operations that we have on numbers. So the familiar operations of addition, multiplication, division, whatever. What do I mean by that? What do I mean by how convergence fits with those operations? Well, a result like this. Suppose we had two convergent sequences, an and bn. The limit of an was some number a, and the limit of bn was some number b. Well, out of those two sequences, an and bn, we could form a new sequence. And the new sequence would have terms defined by this expression here, which we call a linear combination of an and bn. This term in the brackets there. So we would manufacture a new third sequence whose nth term was this expression, alpha an plus beta bn. And we'll be able to prove that this new sequence is also convergent, and it has a very nice limit. It has its limit is the same linear combination of the limits of an sequence and the bn sequence. So what you can like summarize this and say when you take a limit of a sum The limit of a sum is the sum of the limits. And we will be able to prove a similar result for multiplication. If you form a new sequence whose nth term is the product of the nth terms of an and bn, so you're multiplying the sequences together in a way, term by term, so you get a new sequence. Well, if the original two sequences were convergent, then so will this new third sequence. And its limit will be, very conveniently, just the product of the two limits. So those two results in particular, when you focus on them, think of this one as applying. You can think of alpha and beta just being 1 to simplify it. This is saying the limit of a sum is the sum of the limits. Because the limit of a sum is what's on the left-hand side, and on the right-hand side you've got the sum of the limits. And this one here for products, on the left-hand side you have the limit of a product of two sequences, and on the right-hand side you have the product of their limits. So it shows in a way that the operation of taking a limit of a sequence can kind of change, can kind of move past the arithmetic operations of addition and multiplication. So the two fit together extremely well. It's not as, you know, if this wasn't true, or you know, if they didn't fit together so well, then maybe you could have two convergent sequences, an and bn, and when you multiply them together, you get a new convergent sequence, which is a limit totally unrelated to the limits of the two sequences. So then it would appear that the limit process and multiplication of sequences have no relation whatsoever. But that's not the case. They do fit together extremely well. So these are things we want to prove. We want to give rigorous mathematical arguments. And the definition we've given so far, which was definition 1.5, while it is correct, it does convey the right idea, but it isn't very sophisticated, because it relies on this idea of talking about something getting closer and closer to something else. The sequence elements getting closer and closer to the limit as the index n gets closer and closer to 0. Okay, but this idea of getting closer and closer to, it's not wrong, but it's a bit hand-wavy. And what we've seen with these graphs is that different sequences get closer and closer to 0 in very different ways. They do so at different rates. Okay? So 1 over n, the blue sequence is approaching 0 in a certain way. And there are lots of other sequences that do so much faster than the one underneath it. And there's plenty of other sequences that converge to 0 at a much slower rate. So they're not all converging to 0 in the same way. Or they're doing it differently. But at the moment, our definition kind of just squashes all that different behavior together and says, well, they're all getting closer and closer to 0 as the index n gets larger and larger. So that's something we need to make much more definite. And this is how we do it. So thinking of these pictures here, but we're just going to draw a sketch. I'll show you my sketch now in a minute. So what we're approaching now is the formal definition of convergence. We're going to motivate it or introduce it with a bit of a sketch. Maybe try just experiment with capturing this on the camera. So the axes I've plotted here are doing the same thing that of the plots of 1 over the power of n that I'm showing you shortly. So we're going to look at a sequence xn converging to L as n goes to infinity. So the horizontal axis is the increasing values of the index n. 1, 2, 3, etc. And the vertical axis is we're plotting just the value of n. And so the limit is going to be here somewhere. And just so I'll stick down some dots just to suggest just to kind of indicate or suggest some convergent behavior. So the red dots are plotting the values of the sequence elements. And it kind of looks like they're getting closer and closer. They're settling down, getting closer and closer to the value element. Now there's two aspects of how they're doing that. Or there's kind of two parameters we need. And they're traditionally denoted by epsilon and n. So this is epsilon. Lowercase epsilon, it's a Greek letter. This is traditionally used for what I'm going to use it for, and that's just the normal capital N. So what epsilon is a little radius we put around the limit L. So this quantity here would be L minus epsilon, and this would be L plus epsilon. And what we want to be able to do, if this sequence is indeed converging to L, here's the formal definition. If somebody gives us any positive value of epsilon, we're thinking of epsilon as a small positive quantity. And where it fits in the picture is it's a interval. It's the radius of an interval around L. You know, again, normally you think of radius as being to do with circles, but an interval is a one-dimensional disk, if you like. So you can still use the term radius. So epsilon is the radius of this interval, the distance either way from the center point of the interval. This is how the definition works. Given any value of epsilon, there exists an n, let's call this an integer n, exists an integer n greater than or equal to 0, such that for all little n greater than or equal to n, the absolute value xn minus L is less than epsilon. Now, it's quite a mouthful, right? It's quite a complicated sentence. It's a long sentence, and it's got lots of parameters in it, lots of maths in it. But this is the formal definition of convergence. And you need to, don't worry if you're looking at it saying, oh my God, what's that? I don't understand it. You know, it's like seeing a poem for the first time or something. You don't understand the poem instantly. You get bits of it, you have to live with it for a while, you have to interrogate it, think about it. It's similar to something like this. But I'll do my best to walk you through it now and to explain it to you now. So this is the formal definition of convergence. So xn converges to L as n tends to infinity. What this means is, given any value of radius here, there must exist some point, according to my diagram, the corresponding capital N to this value of lambda, which I've sketched, just this value of epsilon, excuse me, which I've sketched here. Well, the value of n, as suggested by the diagram, would be about there. Because from this point on, as suggested by my sketch, from that point capital N on, the sequence elements are all living within the interval between L plus epsilon and L minus epsilon. So from this point onwards, these xn's seem to be, or they look to be from the diagram, they look to satisfy this inequality. The distance from the sequence element xn to the limit L is less than epsilon. Because the dots are all between these two blue lines, at L minus epsilon and L plus epsilon. Over here, maybe not. So some xn's or some xj's, you have xj minus L being greater than epsilon. Some of them are, well, actually, let's stick in a few that are. So some of them are within distance epsilon, but some of them aren't. Some of them haven't gotten within distance epsilon of L. What at least is suggested by the sketch, given this value of epsilon, there seems to be some value of n such that after that value, all the sequence elements are trapped within this. And well, in order for that actually to be correct, all of the infinite rest, the rest of the sequence must stay within these lines. But it's important to recognize that the definition is not just talking about this particular value of epsilon. It's saying given any epsilon whatsoever. So someone could then come along and say, well, okay, looking at the sequence, okay, eventually it does get within a distance, whatever this is, it gets within a distance 2 of L. But what if I wanted it to get within even closer to L? So if they made the epsilon smaller, they made the radius of the interval smaller. Well then, if this sequence was converging to L, you would have to be able to find a number further down. So, because supposedly if they place this smaller interval around L, maybe that would leave out some of the dots. So some of the dots would be inside that interval, but some of these dots, which previously qualified, would now no longer be close enough to float. So you would have to go further down the sequence to find the point at which it became true. Okay, so that's on the screen. I've got a bit of a another demonstration on the computer to show you. And I'll share this worksheet, so if any of you do want to experiment with this afterwards, you can. So this is a little demo of how this definition is working as well. Let me just get rid of some of that. So what's going on here is I've got a few input boxes I can use. Again, we see one of these plots of the sequence elements. I'm dealing with the sequence AN, and it's defined to be 1 over n. The current value of epsilon I'm using is 0.1. And n min and n max are just the minimum and maximum, the starting and ending points of the index n. Just so that describes the portion of the sequence I want to see. So you can see that for this value of epsilon, and then the interval is shown by this shaded region here. Remember, this we already said the sequence is converging to 0. So for this value of epsilon, the sequence is not yet within the interval, because all the blue dots are outside the shaded region around 0. So you have to look a bit further down the sequence. You can see, well, when it gets to n equals 10, it's just about into it. So if let's go from 15 to 25. So what this will do, it will update the graph. So here now the graph is just showing x15 up to x25. So 1 over 15 through to 1 over 25. And you can see, yeah, we now seem to have the sequence completely within the interval epsilon. So the whole shaded region now is from 0 plus 0.1 to 0 minus 0. So yeah, this seems to be converging because it's trapped within this interval. But of course, someone could come along and make the value of epsilon smaller. So they could go 0.001, make it very small, say. Now the graph makes it appear like the sequence is far away from 0. Of course, it's just stretched out the vertical scale. The vertical scale is now that much finer. It's just zoomed in, if you like. But yeah, it looks like our sequence is well away from this interval around the limit. So you have to wait around longer until the sequence gets inside that interval. So you have to search for a larger n. Maybe you have to go up to 100 to it, or maybe go 80 to 100. No, you're still not there. You have to go even further. You have to even go even further down the sequence to find that the sequence is getting inside that interval. Maybe between 500 and 600. No, you're still not there. Of course, you see, I've made epsilon. This is sequence 1 over n. I've made the epsilon equal to 1,000. So yeah, we're going to have to get beyond 1,000. So I think when you go 900 through to 1,100. You may get little errors when you're just fiddling around with the input boxes, but once you've, yeah, you can see. So we're going from 1 over 900 to 1 over 1,100, and indeed at the point 1 over 1,000, the sequence does make it into the interval of distance epsilon around the limit point 0. Okay. So I'll put the link to this worksheet up in the comments to the video, so you can click into it. You'll have to set up an account. You can get free accounts on this online computer system, Sage, and you'll have to do a bit of playing around with it to get into it to make it work. But it's an attempt to give you something visual and interactive to explore this definition of convergence. Any questions about it? Or anybody like to ask anything about it or query me on some aspect of it? So you should try and appreciate how this formal definition of convergence we've just seen, I'll go back to this, it is just saying the same thing that we said in definition 1.5, that the sequence terms get closer and closer to the limit L as the index n gets larger and larger. This is what we wrote there. But it does so in a much more technical way, in a much more precise way, and it attaches parameters. The epsilon parameter is attached to this phrase getting closer and closer to the limiting value L, and the capital N parameter is attached to this phrase as n increases, or as n gets large, as the index n is getting larger and larger. Okay, so the formal definition is there in the notes. It's a bit more of an introduction to it. And what we're going to do in the next lecture or two is use that formal definition to construct proofs of these facts about convergence. Okay. But we're really interested in interrogating and investigating the concept of convergence itself. Okay. So let me just spend a few minutes doing a little example. We're just doing a little bit of work on paper about this 1 over n example. And then, as I say, I will let you go by 10 to, but don't fly out earlier because I've got these things to hand out and I've got an extra problem sheet to hand out to you as well. Okay, so what we're going to do now is we're going to prove that 1 over n does indeed converge to 0 as n goes to infinity according to the formal definition. I mean, it's easy enough to appreciate that it is converging to 0. So as n gets larger and larger, 1 over n gets smaller and smaller, and you can make it as small as you want. And really, the argument is indeed just that, but we're just trying to put a little bit more, just formalize the argument and make it with reference to this formal definition of convergence. So have the definition open beside you, definition 1.6 on page 6. And this is what we have to do. Somebody gives you an epsilon. Or another way to think about it, we have to come up with an argument that can deal with any epsilon. So if epsilon is a positive number, we need to find an integer n such that for all n bigger than n, little n bigger than large n, the absolute value of 1 over n is less than epsilon. Or equivalently, since 1 over n, since we're only talking about positive values of n, this just simplifies to 1 minus n has to be less than epsilon. There's no dealing with positive or negative quantities here, because 1 over n is always going to be positive. In the graphs you always saw was always above 0. See, because look at the formal definition. The formal definition says, given any epsilon, we can find a positive integer. Or more formally, it would be written, there exists an n. Well, if we want to prove it, we have to prove that it exists. We have to summon up this integer, capital N. Anybody got a candidate for what capital N should be? How do I manufacture capital N? But you see, I can use the epsilon. Epsilon has been given to me. Somebody has set the length of this interval around 0, which is epsilon, or epsilon over 2. So how do we find capital N? And we can use epsilon in its construction. Okay. So we want to arrange that this is what we need to show. 1 minus n is less than epsilon. Okay. But you can rewrite that. I mean, you can, both n and epsilon are positive quantities. So this can be rearranged to 1 over epsilon is less than n. So a little bit of trickery, cross multiply. 1 over n is less than epsilon, that's equivalent to saying 1 over epsilon is less than n, given that both n and epsilon are both positive quantities. So now it becomes clear. If we want to arrange that 1 over n is less than epsilon, all we need to do is arrange that the index n is bigger than 1 over epsilon. So we can simply say, so as long as we choose, if we choose capital N to be the smallest integer, it doesn't have to be the smallest one, just any integer really, any integer bigger than 1 over epsilon. From that point on, from this point on, so whichever is the next integer after 1 over epsilon, epsilon doesn't have to be, epsilon, 1 over epsilon won't be an integer. It will be a fractional number close to 0. Sorry, epsilon will be a fractional number close to 0, so 1 over epsilon will be a very large number, not an integer. No, it could be an integer. It could be an integer, but it doesn't matter. So the point is, as long as we choose this integer, capital N, strictly larger than 1 over epsilon, then indeed, for all values of little n that are bigger than or equal to capital N, we have n will be strictly bigger than 1 over epsilon, because remember, capital N is strictly bigger than 1 over epsilon. And we've already remarked that n being strictly bigger than 1 over epsilon is equivalent to 1 over n being less than 8. So we've satisfied the definition. So this argument on the page, this shows that definition 1.6 is true for the sequence 1 over n, i.e. 1 over n converges to 0. It's true for the sequence 1 over n with L, so the value of L we were using, L equals 0. So 1 over n converges to 0 as n goes to 1. And why is what we have on the page? Why does that show the definition 1.6 is true? Because here somebody gave you an epsilon, and there we showed that an index, capital N, with the required property existed. You just look at the quantity 1 over epsilon, which would be very large, epsilon is very small. You just choose the next integer that follows that. Okay. So I'll just stop it there. While I'm